we can design, simulate and test digital circuits using hardware description languages running on a hardware simulator. So a HDL, or hardware description language, is just a description of the actual circuit schematic. So it's made up of two parts, or two sections, a header and a parts section. So the header defines the interface of the circuit, so basically what its inputs and outputs are, and the parts section lists the parts, so the other chips or the other logic gates, what's kind of inside of the circuit. So the interface is basically the external perspective of the chip. So it's the external inputs and the external outputs. And then when you look at it this way, once you know the interface, you can basically treat the inside as just a black box. So we don't actually care about, once we designed it, we don't actually care about the implementation. The implementation is just the internal perspective of the chip. So the actual architecture of the gates that make up the chip, and there's what's going on inside this black box. So when we're actually designing the chip, we're actually designing the implementation. But once we've done that, we just need to know the interface, and that will tell us, how to interact with that chip. So that's what's given in the API, so application programming interface. So you're given what the inputs and outputs should be, and what the functionality of the chip should be. Then you need to use your knowledge and your imagination to come up with the actual implementation of the circuit. So look here for this example. So this just shows an external interface. So it's a black box. We don't really know what is going on inside. So we've got two inputs, obviously A and B. So now we obviously draw the inputs on the left with arrows pointing in, and the outputs on the right. So we've got a single output Y. So this interface, we can just say we've got two inputs A and B, one output Y. Well, this is, if we consider this to actually be an XOR gate, we can actually, the actual implementation of the XOR gate is inside. So we know this externally is an XOR with inputs A and B and output Y, and the actual inside, so the actual implementation, we know that it's given by these this combination of logic gates. So when we're writing hardware description language files, we do it using a text editor, and you're normally given what we call a stub file. So this is the file, it's got some kind of text already in it, and you need to add in essentially the missing parts, which is usually the implementation. So here this would obviously be an example for a NOT gate, so typically be called not.hdl, so the HDL file type. So we can see there's different, we've got some text in here. So this top part here is a chip name. So here we're defining a chip called NOT. Then this top part here defines the interface. So here we've got one input, obviously called in, and an output called out. And then underneath this part section, for this part here, is into implementation. So this is where you need to put the HDL code, and this is where you do the implementation. So we know actually for a NOT gate, we know that we can implement a NOT gate by getting a NAND gate and connecting the inputs together. So here we'd have the input in and the output out. So that's the interface to the NOT gate. So we know that's functionally equivalent to a NOT gate. And the parts then, we know it's made up of a NAND gate. So if this is A and B of the NAND and then out, essentially to just connect these up. So it's the A input of the NAND gate is connected to in, which you can obviously see here. B is also connected to in, and then out is just connected to out. So NAND is a built-in chip. You don't actually have to implement the NAND gate. In reality, a NAND gate is built from transistors, but in this course, the NAND is a built-in chip. It's already been implemented from us. We don't need to implement it ourselves, and we can just build the other logic gates from the NAND gates by specifying the different connections. So parts. So the parts here can be implemented in any order. You know, when we think about procedural programming languages like C or Java or whatever, we know the code kind of executes line by line. But HDL is not, it's not a programming language, it's more of a scripting language. It's just a pure descriptive method of describing how to connect the gates together. So it doesn't actually matter which order you describe the connections, as long as you obviously describe all the connections that exist, the actual order of them doesn't matter. But it is recommended to develop a consistent style for these internal pin names, for this example here. Later on, so in some other parts, we might want to connect this output of this NOT gate into the input of another gate. So for example, if we've got that NOT gate, we might want to put that into an AND gate or something. So later on we would have AND, and might have A equals. So I'm calling this, if this is going to be A, then it's much better to use a descriptive name like not A. So I know this is called not A, and then that feeds into this AND gate. So later when I do, if this is a input for the AND gate, A equals not A, it's much more obvious where this connection has come from. So you use descriptive and consistent styling name for your internal pin names. It makes it much easier. So a chip output, we need to be careful when we're defining multiple outputs, because a chip output cannot directly connect to a part input here. So for example, for this chip, I've just called it widget, we've got an output called out. So this is, so for this chip, we've got our widget, we've got A, and we've got B, and we've got out. So we cannot, this connection out cannot go directly into an input part. So if we've got a different parts here, so in this example, I've called one foo and one bar. So let's say this is foo and bar. Out cannot, this name out cannot be used for an input into one of these parts. We cannot do that. But we can define a separate output. So for in this case here, so bar, I've got the inputs A equals B, B equals foo out. So I can see, so because I've used this descriptive name, it's easy to see. So A, so A connection for B is connected to the B input. B is connected to foo out. So I can see this is foo out is from the output of foo. So that feeds back into here. And then for bar, I've got a one output call, I've called it bar out. So because bar out is going to feed back into here. So I wouldn't be able to use out for this. We cannot do that. So that's why I've had to define a separate output. So here we've got our two outputs. So they're both defined. So one is called out, which connects to here. The external output, so that's this one. Then we've got another output, what I've called bar out, which then feeds back into foo. So you cannot connect this external output to any of these inputs. You have to create a separate output. And you also need to avoid feedback loops in parts. So you cannot have, if you got a part, for example, you cannot have an output for a part feedback into the same part. So you need to avoid using feedback loops. So moving on to buses. So buses are just a collection of conductors. Essentially, let's move individual bits around in parallel. So if you've got eight bits, you need 8 separate wires in your circuit to move those 8 bits around in parallel. So there's one bus line per bit. So the hat computer is a 16-bit machine. So in this case, most of our buses will be 16 bits, and we're going to come across them lots and lots over the course as you build up the hat computer. So we need to know how to deal with the buses using HDL. So you can do it very similar to how you access elements in an array in the C programming language, these kind of square brackets in the syntax. So say if you had a 4-bit bus called A, for example, so this bus overall was called A, you'd say that would be A0, A1, A2, A3. So you can access individual lines on a bus by specifying the index of that. And then you can also tap off kind of just a few lines from a bus. So for example here, so say we've got a part called Wiz. So Wiz has got a 5-input bus. So if this is our part Wiz, got 5 input bits on a bus, and we're going to connect up to this something called bang, and this has actually got 16-bit. So there's 16 bits there. We actually want only, for this example, say we wanted to connect those bits 8 to 12 of bang connected to 0 to 4, so it'll be something like this. You can just specify a kind of sub bus. So here, so the output for bang, the output are defined. So bits 8 to 12 are defined as bang out, and then on the Wiz input, I can just assign it to that. So we're just assigning these bits 8 to 12 into the input bus of Wiz. So that's how we use sub buses. We can all do this on inputs. So for example, in this example here is a part called cods. So this has got 8 inputs. So bits 0 to 2 you want to connect to A, say, so A will be a 3. So then we could say, right, those 3 are A, just by specifying it like this. B, bits 3 to 7 will be connected to B. So by using this syntax, we can just specify particular bits of a bus. And then we can also use constants true and false as well, because sometimes you want to, if you want to set every bit on a particular bus to be a 1. You can just say true. So that means bits 0 to 7 will be true. So we'll have we'd have 8 ones, and then bits 8 to 15 will be false, and we'd have 8 zeros. So the constants true and false we're just used to set logical 1s and logical 0s.